Regarding quantum physics, it's a bit frustrating for those of us who don't have access to certain labs and universities where they perform all kind of experiments using devices for measurements of the subatomic world. And it's a bit frustrating for us because we don't have the chance to do it at home, let's say. However, there are a few situations where actually we can perform this. For instance, in this case, I chose a gold coin, which has 1 ounce. And we can find out how many atoms a gold coin like that has, what is the size of the atom, and also what is the weight of the atom and even of the proton. Alright, so we can do it just based on some calculations, using some calculations here, knowing this number, which is quite incredible, 6.022 times 10 to the power of 23, the Avogadro constant or number, and also the Mendeleev table, which shows that the gold in the Mendeleev table, the symbol is Au from Latin aurum, and it has 79 protons, and the atomic mass is 197, which means it has 79 protons and 112, I assume, I'm sorry, 118 neutrons. So altogether, so that's why the atomic mass is 197. Knowing this stuff, knowing the informations from the Mendeleev table, which we can find anywhere on the internet, and the the Avogadro number, we can calculate all that stuff. And let's do it right now. So, if according to the atomic mass and Avogadro number, we know that in this case 197 grams of gold will contain this number, the Avogadro number of atoms, which is a huge number, of course, 6 followed by 23 zeros, atoms. Now our coin, let's say it's only 1 ounce, which is 31 grams. So how can we find out how many atoms this coin has? It's very easy. We have a ratio here, 197 over 31 should be equal to the fraction of Avogadro number over our number, which we need to find out. And we can use cross multiplication here. It's a simple equation, but I hope you know how to solve that. You can do a cross multiplication, 197 times n equals 31 times this. And from here we divide by 197, we get the number is 31 times the Avogadro number over 197. Using a calculator, we get this number, 95 times 10 to the power of 21. So that's the number, 95 followed by 21 zeros is the number of atoms in a gold coin of this size. Now let's see if we can find out the size of the atoms, of the gold atoms in this case. So first of all, if we melt the coin, I got this information from some jewelers. The volume, and melt the coin and make it a little cube, the volume will be 1.61 centimeters cube, which I converted into 1.61 meters cube, 10 to the power of minus 6 meters cube, because 1 cubic meter has 1 million cubic centimeters, so that's why I have here minus 6, the 6 zeros over 1 million. Okay, so we know that the volume of the coin is this number, and we know that it contains this number of atoms. How can we find the volume of the atom? Of course, we divide the volume of the coin by the number of the atoms, and that will give us a small cube of the atom, where the atom supposedly is a sphere is inscribed in that cube. We have to find out what is the size of the cube. The cube has length, width, and height all the same, right? So the side is, the volume of this small cube is s to the power of 3. The volume of the atom is s to the power of 3. We have to find out the s. And in this case, s to the power of 3 is the volume. We have to divide all the volume of the coin divided by the number of atoms, and we get this number, 17 times 10 to the power of minus 30. It was 0.17, anyway, I changed that to make it easier to extract the cubic radical here. And in order to find the side of this little cube of the atom, or the diameter of the sphere, is the same thing in this case, we have to extract the cubic root from 17 times cubic root of 10 to the power of minus 30, which can be written as 10 to the power of minus 10, everything to the power of 3. In this case, we multiply 3 by minus 10, it's minus 30. Okay, so it's easier in this case. According to the calculator, the cubic root of 17 is 2.58 approximately, times 10 to the power of minus 10. Of course, this 3 goes away here, is cancelled. So that's the size of the, I rewrite it as 258 times 10 to the power of minus 12 meters, because minus 12 is picometers. So this, anyway, this is picometers. Okay, not sure, a trillion of a meter. Anyway, the trillionth part. But this is the diameter, this is the side of this cube, and in fact is the diameter of the sphere of the atom. The radius, which usually they are talking about, is half of it, of course. Half of 258 is 129 picometers. That's the size of the radius of the gold atom. Each element from the Mendeleev table, or each element from the world around us, has different sizes based on the number of protons. So there are atoms of certain elements which are bigger, and others are much smaller. For instance, helium is much smaller, is only 25 picometers. So the gold is 129. All right. Now, what else we can do? We can calculate the weight of the atom, and let's do it right now. Okay, let's calculate the weight of the gold atom. It's quite easy. We know that 197 grams contains the Avogadro number of atoms. So in order to find out how heavy is one atom, we just divide. So let's say atom weight equals 197 over 6.022 times 10 to the power of 23, and using a calculator we get this number, 32.71 times 10 to the power of minus 23 grams. Okay, so this is the weight of the atom. I can do it right now. I can write it. I mean, here the weight or the mass is 32.71 times 10 to the power of minus 23 grams. Okay, so we got these values so far. Another thing is to verify, if we want, how much would be, what's the difference between a, we should find out the weight of a proton. Why not? So we know that we have 197 particles, both protons and neutrons, in one atom, and the atom alone has this weight. So how can we find out the proton? We simply divide proton mass or weight is this number, 32.71 times 10 to the power of minus 23 divided by the number of the particles, and we get using the calculator the following value, 0.16 times 10 to the power of minus 23 grams. Alright, so that's the proton in general, not in gold. Protons are the same everywhere. The gold is different than others by the number of protons, 79. But it's interesting. And also let's mention what is the electron mass. Is electron mass is 9.1 times 10 to the power of minus 31 kilograms, they say, which would be 9.1 times 10 to the power of minus 28 grams. We change the exponent here. And now if we divide these two numbers to see what is the difference between proton and electron, we find about 1835, which means the proton is almost 2000 times heavier than the electrons. That's why we consider the electrons almost close to zero compared to the proton. And this proves that our value we got here of the proton is quite accurate, because that's what the researchers and scientists, they found out, probably using the same procedure or also measuring with very intricate and complex devices. Thanks for watching.